Good morning, everyone. I am Dorian James Colling, and I'm here to present Gauss Jacobi and the Crouts method and how my programs work. No, so before we start for the programming languages, allow me to present the topic, which is the Gauss Jacobi and the Crouts method formally or the definition of terms for it. Allow me to share my screen. Okay, Gauss Jacobi and Crouts method. Okay, so for Gauss-Jacobi, iterative methods, Gauss-Jacobi in numerical analysis are based on the idea of successive approximation. This iterative method begins with one or two initial approximation of the roots with a sequence of approximations x1, x2, x3, and so on and so forth. This sequence of roots converges to exact root A for systems of equation A sub x equals b. We begin an initial approximation of solution vector x equals x sub o, by which we get sequence of solutions vectors x sub 1 and so on and so forth. This sequence converges to the solution of x equals a minus 1b. So, short definition of Gauss-Jacobi. No? So, he was made by a mathematician, German, usually, by Carl Gustav Jacobi. And normally, Gauss-Jacobi solves the system of linear equations. Okay? So, when finding the solution on a normal basis, we find the solution of the systems, equation AX equals B. We assume that the systems of equation have unique solution and there is no zero entry among the diagonal or pivot elements of the coefficient matrix A. So for the first step, we're gonna categorize and we're gonna pull out the x sub 1 for each one, for each linear equation. Next, x2, and so on and so forth. Our next step would be by making an initial guess for the solution x sub o and substituting these values and only to the right-hand side of the above equations. We get the first approximation x sub 1 by continuing by this process, no? This part. Continuing this process iteratively, we get sequence of approximations such as that as k to the infinity. This sequence converges to exact solution of the system of equations to a given error tolerance. No, so this is the convergence approximations. The sufficient conditions of the convergence of the approximations obtained by Jacobi methods is a system of equation is diagonally dominant. That is the coefficient matrix of A. So let's move on to our next topic, which is I'm going to present my code now. So wait, and just pull it up now. Okay. Allow me to share my screen for the. So I've used a online compiler called Programmis. It is usually used to run basic libraries, run basic codes, and run problems that it's in this library. Okay. So since it's an online library, some other libraries may not function. But in case of that, our libraries here or our library headers, no? This G, iOS stream, vector, and CMAT usually is providing the availability of our code here. No? So we can also use Visual Basic, C++, or maybe Arduino code since it's mostly based on C++. No? So let's explain our lines of codes. So on this part, no, vector double, no. So on this part is we have a definition of terms, no, for the ano, Gauss Jacobi part. So we will assign the vector double, which has many kinds of entry. The vector double double here is assigned here on the latter part. Next, the vector double is assigned to be on this latter part. Okay, so int n is just the size. No, we can also show it here. No, so here we'll just have it on the latter part soon. So we're just gonna define first now. So next would be vector double previous x. So we just we'll just assign the last x version now of this one. Next for this one is the maximum iterations, the certain format of the Gauss Jacobi solution now. Okay. Yeah. Okay. Um for this one, A here is the A matrix where the coefficients of XYZ is being inputted. B here is the vector representing the right-hand side of the equation. For the max iterations here, it's the an integer representing maximum number of iterations to perform. And lastly, for the yeah, that's it. Okay. For the first part is we assign the different types automatically, no? So it determines the size of the matrix, assuming it's a square, and initializes two vectors x and previous x, or the x new, both of the size n, no? It represents the current solution on previous x on the next iteration. Now we have this one. This is the code wherein it is the loop that begins the iteration process with the loop counter iter is just a variable ranging from 0 to max iterations. Now down the nested loop here we can see the double sum and the foursome. The nested loop iterates, or this one, the nested loop iterates over the variables in the system of equations. It's a part of Gauss-Jacobi method and solve for each variable individually for each interaction. Now there's another nested loop wherein it calculates the sum of all terms in the equation except for the one being solved. Now, we're gonna check for convergence error. Now, for the convergence error, after updating all the previous x or the x new, the code calculates the change of error in the solution by comparing it to the last one. Now, if there is a converging error, it prints, it returns to x. I mean, if there are no converging error, then it returns to the value of x. Then, or the last part, if the loop completes all iterations without convergence, it prints a message indicating that the method did not converge and returns to the last computed solution in the vector. Now, for the main function, now we have assigned x 5x plus 1y plus 2z on the equals to 10, then 1, so on and so forth. Then we assign the vector double for this one, Gauss Jacobi, since this is the function that is being called. It assigns it, then finds this one, the solution for this one, then return to 0. Now, that's all the code we need to run. So let's say we've tried to change something on this part, then the other code, then this would work. Converge after 37 iteration. Okay. So this code is you can run it everything, and this is mainly editable code on this one. So for the scope and limitations of this would be uh it should be a 3 by 3 matrix. It 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 should be a and B style of matrix style of this one. The number of iterations should not be a part of the problem since it's a loop, nested loop code. Therefore, it's very natural to understand that this code is mainly for this one. No? So after getting the number of iterations, you get the x1, x sub 2, and x sub 3 of this code. Okay. So moving forward, allow me to share my screen again about the Crouts method. For the Crouts method, definition of terms, in linear algebra, the Crouts matrix decomposition is a LU decomposition, which decomposes a matrix into a lower triangular matrix. On an upper triangular matrix, although not always needed, a permutation matrix, it was also developed by Prescott, Durant, Crout. So this is the steps. Yeah. And I'll show you how it's done in the compiler. Now, for a short discussion for this one, I've tried to solve this by having the same Crouts method. Same method almost. So I've used the same headers, library headers such as iOS stream and vector. So this is the main code for this one. So it's mainly on C++ using the void scout method. So first, the first part, we set the diagonal of u to I. Then another nested loop if and multiply the sum of this one and the sum of this one. Okay. Another loop that's coincided is if the solution would be on the latter part. Now, what we can see here is another piece of code wherein this is the function that system of equations LU decomposition. No, that is called the solve of equations. For the first part, we assign the x and y, and for the latter part would be this one. And then for the main part, it's mainly editable, which is this one and this one and this one. Okay. So for the vector double n, l, and u for this one, is doing the Crouts method. Next would be the solving of the linear equation, and lastly, the output of the solution. That's it for our presentation, and I want to thank you and thank everyone for listening. That's it. Thank you.